Hello again, welcome back. This is our first video lecture for Chapter 8. So, video lecture 8.1. Chapter 8 is entitled Potential Energy and Conservation of Energy. So we're continuing to use energy ideas in dynamics, using energy ideas to explain why a particle moves the way it does. And we're going to introduce a new form of energy in this chapter. We introduced the form called kinetic energy in the previous chapter. Kinetic energy, remember, was the form of energy a particle has simply because it's moving. And the formula for kinetic energy, capital K, is 1/2 times the mass of the particle times the magnitude of its velocity squared. That's kinetic energy, the energy of motion. We're going to introduce in this chapter a new form of energy, actually more than one more new one, but first, the new form of energy we're going to introduce is called potential energy, which is a little bit more abstract than kinetic energy, a little bit more difficult to understand, get a grasp of, but we'll work on it, no pun intended. And then we will use the ideas of kinetic energy and potential energy together to introduce our first what is called conservation law in physics, called conservation of energy. But that will be more in the second half of Chapter 8. For the first part of Chapter 8, we're going to be focusing our reading, Chapter 8, Section 1, all about introducing this new form of energy known as potential energy. Okay, I'm just going to start out with a description of what the form of potential energy is. And then I will give you the technical mathematical definition in a little bit. But first, the description. Potential energy is that form of energy associated with the configuration of two or more objects that interact by means of a special force. That probably doesn't tell you a great deal, yet that is about the best description I can give you at this time. It is that form of energy associated with the configuration of two or more objects, and those objects are interacting by means of what, for now, I will just call a special force. The whole concept of potential energy is mainly an energy bookkeeping device for keeping track of, tallying energy forms. But it turns out it's a very useful bookkeeping device, and we will use it a lot. So we have to become comfortable with it. One of the things that makes it useful, potential energy, is that under certain situations we will find that the energy can change forms. That is to say, it can be converted between potential energy and kinetic energy. And the transfer can go either way. You can go from potential energy into kinetic energy, or from kinetic energy into potential energy. Okay? You can go either way. An example, even though we haven't formally defined anything yet, is if I take a little plastic ball and I hold it at a certain height above the table. As we will learn, we can describe the system of this ball plus Earth, because of their interaction through the gravitational force, as having what's called gravitational potential energy. And if I release the ball and let it fall, the gravitational potential energy will decrease, but the kinetic energy will increase by the exact same amount. In other words, the gravitational potential energy will just be transferred from one form, gravitational potential, into another form of energy, kinetic. And of course, when it bounces off the tabletop, right at the tabletop, it has kinetic energy, but it's going to transfer some of that kinetic energy into gravitational potential energy as it comes upward. So a falling and bouncing ball shows transformations between gravitational potential energy and kinetic energy. And I'll show you a video of that as well. Okay, now, I said that potential energy is associated with the configuration of two or more objects that interact by means of a special force. Well, let's say more about this special force. These special forces, there's only a couple of them that allow this exchange of energy between the two forms of kinetic and potential. And since they are special, they're going to be put into a kind of a category all their own with their own name. And the forces that are special in this regard and allow for the exchange of energy between the two forms of kinetic and potential are known as conservative forces, because they're related to what we're going to call conservation of energy. And in physics, conservation means staying constant. Okay, but for now, it's only what are called conservative forces that allow you to exchange energy between the two forms of potential and kinetic. And I will tell you that of all the forces we've studied so far, 2 of them fit into this special category that we call conservative. They are the gravitational force and the spring force. That's why we spend a lot of time talking about those 2 forces. Turns out they're rather special and important. They fall into this category known as conservative forces. All right, here comes the next big thing. For every conservative force, there is a corresponding potential energy function. Every conservative force has a potential energy function that goes with it. But only these special forces, called conservative forces, have potential energy functions. So, since the gravitational force is conservative, there must be something called gravitational potential energy. And there is. If the spring force is conservative, and it is, then there must be something called the spring potential energy, often called elastic potential energy. And there is. For every conservative force, there is a corresponding potential energy. But if it's not a conservative force, think, for example, kinetic friction, there is no potential energy function that goes with it. There is no such thing as frictional potential energy. Okay? For one thing, you can never convert, if it existed, frictional potential energy into kinetic energy, for reasons I'll explain later on in the chapter. Now, here comes the formal mathematical definition of potential energy. And I hinted that you're not going to be happy with it, but it is the formal mathematical definition, and I'm going to state it now. It's related to this idea I just highlighted, but now I will underline. For every conservative force, there is a corresponding potential energy function. And here's the definition of the potential energy. The change in the potential energy for a given conservative force is defined to be the negative of the work done by that conservative force. So we must be talking about between 2 points. Okay? So if you have a particle moving between 2 points, and work is done on it by a conservative force, whatever that work is, it'll be the negative of the change in the corresponding potential energy function that goes with that force. Okay? We'll build up on that. Okay? I'll give you some examples, but that's the formal definition of potential energy. Note the symbol for potential energy is a capital U. Okay? Capital U is the symbol for potential energy. So this equation in red is talking about the change, delta, in the potential energy, U, of a certain conservative force, defined to be the negative of the work done by that conservative force. Oh, and here's another interesting property of conservative forces. The work done by any conservative force is said to be path independent. It only depends on the starting point and the ending point. All right, since we only know of 2 conservative forces, gravitational force and spring force, and I want you to remember that, those are the 2 conservative forces. I want you to remember that, gravitational and spring. Then the work that either one of those forces does between any 2 specified points doesn't depend on the path you take between those points. Let me try to explain that a little more with this schematic picture. Suppose we're looking at a situation where there are 2 points, A and B, and a particle is going to move from A to B while a conservative force acts on it, maybe gravitational force, maybe spring force. Okay? And first, the particle is going to travel along the curvy path labeled 1, path 1, that goes from A to B. Okay? And we could calculate the work done by the conservative force between A and B along path 1. Okay? And because that's a pretty complicated path with some curve to it and everything, you might feel like that work calculation would be tricky. But nevertheless, let's say we've calculated it. The work done by a conservative force on a particle as the particle moves from A to B along the path labeled number 1. Then put the particle back at point A and let it go from A to B, same beginning and ending points, but now let it take that curvy path labeled 2, which looks even a little bit more complicated than 1. And let's say we can calculate the work done by this conservative force on the particle as it goes from A to B along path 2. What we will discover is that the work done for those two paths is the same. So whatever work was done along path 1 by the conservative force, it's the same work done along path 2. Okay? I'll give you a very brief explanation of how that can make some sense. Suppose, just for the sake of having something in mind, that this is a vertical plane and the plus y direction is upward, and we're taking a particle from A to B along either path 1 or path 2, and we're going to be interested in the conservative force known as the gravitational force. Okay? Well then, I already know the formula for the work done by the gravitational force. We figured that out in chapter 7. Negative mg delta y, the change in the y coordinate between A and B. So, let me denote delta y. Delta y is right there, yes? The change in the y coordinate between point A and B. Well, notice it doesn't matter whether my particle moves from A to B along curvy path 1 or along curvy path 2. It's still going from A to B. And therefore, no matter whether it's path 1 or path 2, the delta y is the same. So the work done by the gravitational force based on that formula is the same for path 1 or path 2 or any other path I might draw, like that one, and call it 3, that goes from A to B. Because any path that goes from A to B will have the same delta y. So the work done by the gravitational force doesn't care about the actual path we take from A to B. It doesn't matter at all. All that matters is what the delta y is. Okay? All right, so that's just one example of the situation where the work done by a conservative force does not depend on the details of the path you take between 2 points. Let me show you one other consequence of that fact. Okay? All right, let me get rid of some of this extra stuff so I don't have so much clogging up my drawing. Okay? All right, suppose I imagine going from A to B along path 1. So there's work done by the conservative force along path 1. And it's equal to the work done by the conservative force along path 2. So let me put that they are equal. Now let me write it like this. The work done along path 1 minus the work done along path 2 must equal 0. But now let me imagine this. The particle goes from A to B along path 1 and then goes from B to A along the reverse of path 2. So that it ends up back at point A. It just made a kind of a loop back to where it started. It's called a closed loop or closed path. Well, the work to go along path 2 from B to A is just the negative of the work when you go along path 2 from A to B. And the work to go along path 2 from A to B is that. But that's just the negative to go from B to A along path 2. So the work to go along path 1 from A to B plus the work going along path 2 from B to A equals 0. But that's the work around a closed path. So the work done by a conservative force when you go around a closed path, starting at a point and ending back finally at the same point you started with, is always 0. Okay, so talking about properties of conservative forces and the definition of potential energy. Now let me show you a couple of YouTube videos motivating the two forms of potential energy that we're going to be using. Gravitational potential energy to go with the gravitational force, and elastic potential energy to go with the spring force. And I want to show you situations where one of those forms of potential energy is converted into kinetic. Okay? All right, so now let me go over to a YouTube video. This is showing, I think it is. And this is an animation of a device called a pile driver. And it uses this big weight called the driver, and it's going to lift that driver up above the ground. The system's going to have gravitational potential energy, and then drop it and let it fall onto the thing called the pile. So it's going to convert gravitational potential energy into kinetic energy, and then it's going to use that kinetic energy to do work on the pile and push it into the ground. So let me run the animation. All right, the driver is lifted. It has gravitational potential energy. It's converting that to kinetic energy, which it then uses to do work and drive the pile into the ground, pulverize it, then they put in the rebar for extra support, and then they pour in the concrete and let it dry. And they're well on their way to making a foundation for some kind of a building. Okay? So in a pile driver, we're converting gravitational potential energy into kinetic energy. All right, let me show you another situation. This is a YouTube video where people are converting elastic potential energy from bungee cords that act like springs into kinetic energy. And I don't need to show you the video for this because they're not saying anything that enlightening. But I want you to just watch what they're going to do. You can see she's connected there with two bungee cords. Think of them as acting like springs between two poles. And this person is explaining to her what's going to happen. And then they're going to stretch the bungee cords, like stretching a spring. So now we have elastic potential energy, more and more and more and more of it. And now we convert it to kinetic energy. Then we convert it to potential energy, then back to kinetic, then to potential, then to kinetic. Back and forth and back and forth. Okay? We're converting energy between the two forms of elastic potential energy and kinetic energy. Okay? All right. Now, moving on. Let me talk a little bit more about where this expression that the work done by a conservative force equals the negative of the change in the corresponding potential energy. Let me apply that idea to the gravitational case. That's a conservative force. The work done by the gravitational force will equal the negative of the change in gravitational potential energy. Let me apply that to something specific. Here somebody in this drawing has taken a tomato and has just thrown it upward. Let it go up to some maximum height and fall back down. Let's imagine the upward journey. Okay? The upward journey. And let's consider whether the work done by the gravitational force for the upward journey is positive or negative. Gravitational force is a constant force, so the work would be F grav dot delta R. Let's make some sketches. From release point to high point, there's the delta R, but the F grav, of course, is down. So the angle between them when they're drawn with a common tail, phi, is 180 degrees. And when we do that dot product, we'll have mg delta r magnitude times the cosine of 180. But the cosine of 180 is -1. So my conclusion is on the upward journey, the work done by the gravitational force is a negative number. According to this expression up here, then, the change in the gravitational potential energy must be a positive number because of that negative sign. But that's exactly what that means if the tomato is higher. It has more gravitational potential energy than it did at the beginning. Okay? So the negative work done by the gravitational force has shown up in an increase in gravitational potential energy. Now what about the downward path of the tomato? Okay? Let's think about whether the work done by gravity is positive or negative. What do you think? You can pause the video if you want to. Downward journey of the tomato. Is the work done by gravity positive or negative? Well, the delta R, the displacement would point down, but so would F grav. I'll draw the F grav and the delta R with a common tail. There's F grav. They both point down. So in this case, the angle phi is 0. And when I do the dot product, I'll be taking the cosine of 0, which is +1. So the work done by the gravitational force on the downward journey is positive. That tells me that the change in the gravitational potential energy for the downward journey is negative because of that negative sign in the relationship that's circled in red. So for the downward journey, gravitational force does positive work, but the gravitational potential energy decreases. Well, that's because it's getting lower. Okay? Let's apply this thinking to the case of a spring force. The work done by the spring force is the negative in the change of the elastic or spring potential energy. Okay? Let's apply that. I'll at least apply it to the case you see here in this picture. Block on a horizontal system with a spring with some spring constant K. And 0 is equilibrium. Let's say that's where it started from, right there. That's x1, so x1 is 0. And here we are at point x2, and we can clearly see that the spring has been compressed. We have a formula for the work done by the spring force. It's k over 2 times x1 squared minus x2 squared. Remember, x1 is 0. So this is going to be a negative number. Yes, the work done by the spring force when you're compressing it is negative. You're ending up farther from equilibrium, right? The work done by the spring force is negative. That must mean, because of the negative sign relating them, that the change in the spring potential energy is positive, greater than 0. The spring potential energy increases. But that's exactly what we mean when we say a spring gets more and more compressed. The more you compress a spring, the more spring potential energy it has. Okay? Okay, so I'm just trying to show you, for the two cases of gravity and spring forces, how the relationship between work and change in potential energy has that negative sign in there. When the work done is one sign, the change in the corresponding potential energy is the opposite sign. When the work done is positive, the change in the corresponding potential energy is negative. The potential energy decreases. When the work done is negative, the change in the corresponding potential energy is positive. The potential energy increases. Okay, with all that in mind, I am now going to state for you two key potential energy formulas that we are just going to use. If you want to have a greater understanding for where these formulas come from, and I don't blame you if you wish to do it, but I'm not going to go through it in this lecture, then you read Chapter 8, Section 1 in the book. And you will see that they use this relationship, that the work done by a conservative force equals the negative of the change in the corresponding potential energy function for that force, to derive the following two formulas. We will just use them. We just have to make sure we use them correctly. The function for gravitational potential energy labeled U sub g. It has a very simple form. Take the mass times little g times the y coordinate of the particle. That's assuming that we have taken a plus y axis vertically upward, and somewhere on there we have chosen an origin and labeled it y equals 0. Okay, so we have a plus y axis vertically up. Somewhere on that we have chosen an origin and labeled it y equals 0. And then relative to that axis we have some particle of mass m. At a given time its coordinate is y, so its gravitational potential energy is m times g times y. And it could be located, this particle, below the origin. Maybe depends on where the origin is. And even if the origin's on the ground, maybe the particle's down in a well or in a hole of some kind. Yeah? So depending upon what the y coordinate value is here, the u grav could be a positive number or a negative number, depending upon whether the particle is located above y equals 0 or below y equals 0, wherever y equals 0 was chosen, and that tends to be up to us. I recommend you do not say this formula for u grav as m times g times height, because that might lead you to think that it can only be positive. Height kind of implies only positive. It's m times g times y coordinate. And the y coordinate of a particle could be positive, negative, or 0, depending upon where the particle is relative to the origin. So we're going to use that formula whenever we need to calculate gravitational potential energy. And by the way, this gravitational potential energy is stored in the system that consists of the particle with the mass m plus Earth. That's what gives us the gravitational force, so you need to include the Earth. Okay? So when we talk about gravitational potential energy and use that formula mgy, we really mean for a system consisting of the particle of mass m and Earth. Now, the other potential energy function is elastic or spring potential energy. And the formula we'll use for that is U sub s equals 1/2 times little k, the spring constant, times x squared, where our reference point of x equals 0 is where the spring is unstrained, neither stretched nor compressed. Okay? So here we're talking about a situation much like up above in the drawing. Up here of the block on the horizontal x-axis and the spring constant k, and here it is at some time at location x with equilibrium at x equals 0. Then the formula for the spring potential energy is 1/2 kx squared. Note then that the x here represents how much we've compressed the spring. You could also use it if the block were on the left side of the origin, in which case we would have a stretched spring. It still works just fine. And notice this formula, 1/2 times little k times x squared, can never be negative, the way we've got this expression. So unlike the formula for U gravitational, U spring can never be a negative value. Now please note, though, the restriction for this formula. It's for the block moving along an x-axis, and the reference point has been chosen to be the origin of that x-axis. It sometimes is useful to have a more general understanding of what elastic potential energy is, and that is this expression right down here. That the form for U elastic is 1/2 times the spring constant times the amount of deformation of the spring squared. In other words, how much has it been compressed? That's deformation. Or how much has it been stretched? Either one. Take 1/2 times the spring constant times the amount of deformation squared. That's what U elastic really means. Okay, so what I want to do for the last bit of this video lecture is a little more practice. Let's focus for now on gravitational potential energy. Okay? All right, so we're going to practice a little bit with gravitational potential energy. And in this figure below, we have a simplified version of a roller coaster. And we're treating it as a particle, that's the roller coaster car, of mass m equal to 825 kilograms. Okay? And it's going along on a frictionless surface. The track is frictionless. And it has just topped out at the first hill there at a speed of 17 meters per second, where its vertical height h above the ground, as you can see in the picture there, what the h means, is 42 meters. The questions are as follows. How much work does the gravitational force do on the car from that first starting point, right here, the starting point, the top of the first hill, to these various points? First, point A. Okay? All right, so let me just kind of write down over here on the side how we're going to do this. This is asking us to calculate WG, so I'm going to go straight to the formula derived in Chapter 7 for calculating WG, work done by the gravitational force. Negative mg delta y, where our y-axis is vertically up, so I just take negative m times g, and then I put in the parentheses here the change in the y-coordinate from the starting point to the top of the next hill there, which is point A. Well, it shows me that the next hill is the same height h as the first hill, so I do think that the change in y between the starting point and point A is 0. So the gravitational force overall does 0 work as the car goes from the first hill down and back up to the top of hill A, even though it moved. That's because at first the gravitational force is doing positive work, and then it does an equal amount of negative work, so the total work done between the top of the first hill and point A is 0, even though the particle moved. B. What's the work done by the gravitational force on the car from the starting point to point B, the top of that hill there, which is only at a height of h over 2. So, work done by the gravitational force is negative mg delta y. That's negative mg times y final, h over 2, minus y initial, h. That's negative mg times negative h over 2. It's two negatives multiplied together, so that's positive mgh over 2. Right? Gravitational force does a net positive amount of work as the car goes from the first point to point B, and the amount is mgh over 2. And now part C. How much work done by the gravitational force as the car goes from the starting point to point C? Point C is on the ground. All right, well, that's easy enough. That's y equals 0. So to calculate work done by gravity, I do negative mg delta y. So I do negative mg times y final, 0, minus y initial h. So this is positive mgh. Okay, and I've calculated the work done. It's positive in going from the starting point to point C. Now, so far no problem, I hope. Now, we're going to take the gravitational potential energy of the car-Earth system to be 0 at point C. And with that in mind, we are to find the value of ugrav when the car is at these various points. So what we're doing is they're telling us, take your vertical positive y-axis and choose y equals 0 at point C, i.e. on the ground. It's telling you where to take the origin of your y-axis, on the ground. With that in mind, start calculating ugrav. Use the formula mgy. Just that, mgy. And what is u grav if you're at point B? It's m times g. And what's the y value when you're at point B? h/2. That's not hard. And for E, what's the gravitational potential energy of the car-Earth system when the particle is at point A? You do mgy, m times g, and when you're at point A, the y value is h, so mgh. All right, now let me show you one more thing. Let me now do a little check. Let me imagine the motion from the starting point to point A. We already found how much work is done by the gravitational force in that case, 0. What's the change in the gravitational potential energy between those points? Between the starting point and point A. Well, they're both at height h, so there isn't any change, is there? So, change in u grav is 0. All right, now let's go from the starting point to point B. The work done by gravity we already found is positive mgh/2. Now let's calculate the change in u grav from the start point to point B. So take the value of u at point B minus the value of u at the initial point. Okay, at point B, that was the answer to part D, it was mgh/2. And at the initial point, it's mgh. So it looks like the delta U is negative mgh/2. What's the point? The W grav is equal to negative delta U grav. Okay? Why don't you try checking that for yourself for the car going from the start point to point C? What was W grav? And what is delta U grav between the start point and point C? And convince yourself that W grav will equal negative delta U grav. And then there's just one more part here, part F. If the mass of the roller coaster car M is doubled, what happens to the change in the gravitational potential energy of the system between points A and B? Well, I just found the expression for that, didn't I? The change in the gravitational potential energy between A and B, it's the same as the change in the gravitational potential energy between the start point and B, is right there. Negative mgh/2. And it depends, here's the key point, it's proportional to m, the mass of the car. So if I double the mass of the car, I'm going to double the value of delta U grav. It depends on the mass of the particle. Okay? Okay, so here we're practicing with gravitational potential energy and the formula for calculating it. Remember the formula, U grav equals m times g times y coordinate, where it assumes a plus y-axis vertically up, and someone, either the person writing the problem or us as the problem solver, it will depend, will have to pick where y=0 is. All right, so we will be practicing a lot with this throughout this chapter, but that's our introduction to potential energy. That's all for this video.